Good morning, all. Am I audible? Can you please confirm I am audible? Thank you, Sharanya. So let's wait for some more students to join and then start the class. Hope I am visible to all of you and my screen is also visible. Hello. Hi. Thank you for confirming the screen is visible and my camera is visible. Happy Deepavali to all and very happy Children's Day too. It's a day for celebration together, right? So I know all are in the celebration mood. Yes, football lover. Thanks for asking. I had my food. Happy Diwali. I think all are in the preparation for Diwali and busy with that. Happy Children's Day. It's for all, right? Happy Children's Day. I'm just waiting for some more students to join so that I can start with the class. Today's topic is a very interesting topic. It's about magnetism. Okay. So I have some experiments also with me. So once some more students join, we start with the class and it's a revision class. Yes, football lover. I'm very good and how are you? Thank you for asking. Happy Children's Day, Sharanya. Hi, Leela. Deepavali Shubhashayagalu. Okay, I think we can start with the class now. So I just show my screen and please confirm the screen is very visible. I know my camera is visible now, right? So I want to switch to the classroom mode now. So hope it is visible. Can anyone please confirm it? Okay, okay. So the board is visible, right? Okay. So we're going to start with the revision of magnetic effect of electric current of class 10. Okay. So since already the chapter is discussed and it is a revision class, I would like to show some of those experiments or some of the models related with that chapter, and we will be doing revision together. And if you have any doubt in between, you can type in the chat box. And once I am done with the revision and once I'm done with the explanation, then I will be answering all your doubts. Happy Diwali for the new joinees. Some more are joining now. Very happy Diwali. Happy Diwali and thanks for joining all. Okay, so today's topic is magnetic effect of electric current. Okay, so if you have to learn magnetic effect of electric current, I feel that we need to know what is a magnet. Basically, what is a magnet, right? So in school now no one is able to go to school. I know that very well. But if you go to school, definitely in the school lab you will be seeing the magnets, right? When a teacher teaches you that, they'll be bringing the magnet and showing to you. So I have a bar magnet with me. Okay. So see, when I say magnet, what comes to your mind automatically? Some kind of a feeling, right? What is that feeling? Something which is attracting, right? See, if I ask every time to my students, they used to say it attracts some materials. It will not attract all the materials, but it attracts some of the materials, right? So that's a magnet. That's a very simple explanation, right? So here we are, actually the chapter is about magnetic effect of electric current. So I think my magnet, what I'm showing is visible to you. So this is a bar magnet, and and everyone knows that there is a north pole and south pole for the magnet, right? So how do we identify the pole of a magnet? When you take a magnet, some magnets there will be some color difference from in both the sides, okay? And some of the magnets you can see a dot, okay? So here you can see a dot. This dot is representing the north pole. Okay, so this is how basically we identify a magnet, the poles of the magnet. And the basic property of magnet is the like poles will repel each other and unlike poles will attract each other. When you say like pole or unlike pole, what does it mean? Like pole means when it is of same polarity, right? Same polarity. So north and north. See, I have two magnets now. Two bar magnets are there. So I'm showing you the dotted positions here, right? So these two positions that represents north and north. So I have two magnets and two north poles are trying to I'm just trying to move it together, but I'm not able to do that because I can really feel the force of repulsion here. If you have a magnet at home, you can also try it. Okay, but if I see, if you have seen, see, this is not sticking together, right? This is not sticking together. I'm trying to stick it together, but it's not happening because there is a repulsive force. But at the same time, I'm keeping this north pole here and the south pole of the other magnet. It automatically comes. See, it's just pulling my hand. It's just getting stuck together. See this. That means the unlike poles, the opposite poles attract each other. If I do the reverse way, I'm keeping the south pole of this magnet and the north pole of the other magnet. See, it just comes and stick together. But if I am keeping the north and north together, then they are not going to stick. They are just repelling away. I'm just trying to push, just pull it, bring it together, but they are just repelling from each other. Okay, so that's a basic property of magnetism. Let me show another type of magnet. All of you are familiar with that, but I just want to show you. This is a horseshoe magnet. Okay, so there are different types of magnets. Bar magnet and horseshoe magnet. They are the commonly used magnets in laboratories. Okay, and nowadays you can see a lot of magnets in the toys, right? Spherical magnets are there, cylindrical magnets are there, ring magnets are there, disc like a coin kind of magnets are there. Okay, so that's about the basic magnetism. Here we need to know what is a magnetic field and magnetic field line. Okay, so the basic property of magnetism, let me show once again. See here we have a compass needle. What is a compass needle actually? What is a compass needle? Compass needle, it's a magnet. Okay, it's a magnet by itself, and all the properties of magnets what we learn or what we experience, it is applicable for a compass needle also. So you can see on the screen a bar magnet moving towards the compass needle, right? You can see the red color. Through that red color you can differentiate what pole it is. Okay, so the north and north, the red one is north pole of that magnet, and that north pole is repelling the compass needle's north pole. Okay, so if we use this compass needle to identify or to feel the presence of a magnetic field. So when I say what is a magnetic field, right? See, we know what a magnet is and what is a magnetic field. If I bring a magnetic material nearby this magnet, there will be some region where magnetic force is experienced. Okay, so I have a magnet here. If I have a magnetic material, see, I have a magnetic material here, that means it gets attracted towards the magnet. You can see it is sticking here. So if I bring it here, I can feel, see, this material, this magnetic material is getting attracted towards this bar magnet. Okay, so I'm bringing it away, so still I can feel that force. I'm moving this magnetic material much more away from the bar magnet. But if I'm not that feeling that much attraction, okay, see, I don't know how to explain you that, because it's a feeling when I'm holding. If you have a magnet, really you will be able to understand it. Okay, so what I'm experiencing on my hand, right? I have the magnetic material and the bar magnet. Okay, so there is a space around this magnet where magnetic force is experienced. That is called as the magnetic field. Hope you are able to understand. So the space around the magnet where magnetic forces experience is called as magnetic field. As I said, now when I am showing you, see, I have the magnet in my hand, I have the magnetic material in my hand. I can feel it really. I can feel up to what distance I am able to, this magnetic material is experiencing the force. But how do I show you that, right? For that, we have another trick that is called as magnetic field line. Okay, so magnetic field lines. What are these magnetic field lines? To express or to show the field up to what distance this magnet will be applying a force, or the magnetic material will be experiencing a force. We have the method of plotting the magnetic field lines. Okay, so you can see we will be keeping the bar magnet over a piece of paper. Okay, so this experiment is very simple. See, since I have a magnet, I have a compass needle also, we will be able to plot the magnetic field line. This is very simple experiment. Okay, so what we do is we will be keeping this magnet over a piece of paper, a white sheet of paper, then trace the outline of it. Okay, you have to trace the outline. So why we have to trace the outline of the magnet? See, I'm keeping the magnet here. Say I'm doing the experiment. I'm not going to stick it with the glue or anything. Okay, so there is a chance for this magnet to slip from its position, right? So when after, if it is moving, even if it is a slight movement, there will be a lot of errors in the experiment. Okay, we will not be getting the actual magnetic field plot if you do like that. So we are going to plot the outline, just draw the outline using a sharp pencil, so that in case if it slips from its position, I can bring it back to the initial position itself. Because when the position changes, the magnetic field is specific for a particular point. Okay, so it depends on at what distance is that point, right? Whether it is nearby the magnet or away from the magnet. Okay, so all these things are to be considered. So we're going to keep a compass needle nearby the magnet. Say let's keep it nearby the north pole. So there will be a deflection in the compass needle. Then you can see that in the diagram, right? A magnet is kept, and the near the north pole we are going to keep the compass needle, and the compass needle will deflect. So north pole of the compass will be deflecting away from the north pole of the bar magnet. So we're going to put a dot at that position. Take out the compass needle, keep it over that dot. Dot in the sense it was the position of the north pole, right? So we continue the experiment and we can see it's reaching towards the south pole of the magnet. So then we are going to combine these magnetic field positions, right? We are going to draw a line, or we are going to join those dots, right? So we will be able to plot the magnetic field line. Okay. So what is magnetic field line? It is to represent. Okay. So the path traced by a north magnetic pole free to move under the influence of a magnetic field is called as magnetic field line. So when I say I'm not able to express the feeling, right? See, how do we express a feeling? Like someone is exerting a force, right? We can just say that. Only if you do it, you can feel it. But we have to explain it. Definitely, we are expected to explain what it is. For that, we are using the help of our magnetic field lines. Okay. So the path traced by a north magnetic pole free to move under the influence of a magnetic field is called as magnetic field line. So hope all of these are clear to you. Now there are some specific properties for magnetic field lines. What are the properties of magnetic field lines? Very, very important. See, this magnetic properties of magnetic field lines, it is applicable for all the types of magnets. No matter it is a bar magnet or a horseshoe magnet, but everything, every magnet, whether it is made of electric current, right, electromagnet, whatever it is, all these properties are applicable for that also. So the first property is magnetic field lines emerge from the north pole and merge at the south pole. It emerges from the North Pole. Field lines, if you plot, you can see it is coming from the North Pole and going towards the South Pole. So we say that it emerged. It emerged means what? It comes out of that North Pole and reaches, right? It's going towards the South Pole. It merges at the South Pole. So what do you mean by merging and emerging, right? So that is possible for a circle kind of thing, right? See, if I give you a circle, How do you say from where it starts? Can anyone say from where it starts? See, maybe when I draw the circle, I'll use the compass and I'll be putting the center and just draw the circle. There is a starting point. But when you see a complete circle, it's not easy to explain from where does it start, right? So, similar to this, magnetic field lines are closed curves. This is a closed loop, right? Magnetic field lines are closed loops. Now, another important point is the strength of the magnetic field lines. It is expressed by the degree of closeness of the magnetic field lines. In the previous slide, you have seen the magnetic field line pattern. Let me show that once again. Okay. See, here nearby the poles of the magnet, you can see more concentration of the magnetic field lines, right? So, the degree of closeness of the magnetic field lines indicate the strength of the magnetic field. Okay. So, magnetic field lines are closed curves. Then the strength of the magnetic field is indicated by the degree of closeness of the field lines, and no two magnetic lines intersect each other. Magnetic field lines never intersect. That's a very, very important question and a repeated question in the board exams. It's very simple to answer. Okay, magnetic field lines never intersect. So either the question can be what are the properties of magnetic field lines, or it can be why two magnetic field lines not intersect. So when we were plotting the magnetic field lines, we were following the path of the north pole of the compass needle, isn't it? So when if you plot, if we were putting the dots wherever the compass needle was showing in that at that position, we were putting the dot with the help of a pencil, right? So if magnetic field, two magnetic field lines are intersecting each other, what happens? At that particular point, there should be two directions for magnetic field. Is that possible? Can we go in two directions at the same time? If someone asking you, right? Say you go to school and at the same moment you have to go to the market to buy something. Is it possible? Either you go to the school, then go to market, right? It's not a simultaneous process. It's not together. So at a time, right? At a time, at one point, going in two directions for one person, that is not possible. That's a practical example. So the same is true for magnetic field also. See, if I ask you the magnetic field to go this way and that way together, it's not possible, right? At this point, there will be some specific direction. There in that direction you can go, right? So we can say that the answer is, I'm giving you these examples to understand. So when the answer comes, right? So if two magnetic field lines are intersecting, that means that magnetic field has two directions at a particular point. That is impossible. Okay, or the compass needle has to show two direction, the deflection in two directions. If the magnetic field lines are intersecting, that is impossible. So magnetic field lines never intersect. So the important properties are: magnetic field lines emerge from the north pole and merges at the south pole. The strength of the magnetic field is indicated by the degree of closeness of the field lines. No two magnetic field lines intersect each other, and magnetic field lines are closed loops. Hope it is clear to all of you. If you have any doubts, please comment in the chat box. Okay. Now, how do you identify the polarity of a magnet? So let me take my magnet. This magnet, suppose, see here I have the indication of a dot that represents it is a north pole. But if it is a very old magnet, all the colors are it's faded, or it's all maybe a lot of scratches are there, and I'm not able to identify the polarity. So what I can do is I can suspend this magnet freely. Use a string, just tie it over the bar magnet and suspend it. So when you do that, it aligns in the north-south direction. North-south direction in the sense our place, we know what is north and south, right? There. So in the same direction of north-south, it aligns. Automatically, it will be aligning. See, here I am holding it, so it will not align. See, because I am holding and I am applying a force there, right? So a freely suspended in the sense you have to take a string and just allow the magnet to move freely like a compass needle. So it aligns in the north-south direction. So why it is happening so? Earth has its own magnetic field, right? Earth's magnetic field is very strong, and we can actually imagine there is a bar magnet. Actually, it's not a bar magnet. So we can imagine a magnet within the Earth. Of course, there is magnetic properties. Okay, so the detailed study you will be doing in grade 12. Here we are discussing grade 10 level topics, right? So well, now, for the time being, we are going to imagine a bar magnet within the Earth whose south pole, see, I mean the south pole of the magnet, Earth's magnet is at the geographical north of the Earth. Okay, so and similarly, the north pole of the Earth's magnet is at the geographical south. That means the south pole of the Earth. So it's the opposite of the poles, right? See, the bar magnets, Earth's bar magnets or Earth's magnetic field south pole is at the geographical north of Earth, and Earth's magnets north pole is at the geographical south of the Earth. So when I suspend my bar magnet freely, what happens is the north pole of my magnet is attracted towards the south pole of the Earth's magnet. So what does it show? It will be aligning towards the north direction. So this is the best method to identify the polarity of a bar magnet or any other magnet if no other magnet is given. If I have two magnets, okay, I can try. Right, I can just try it is repelling or attracting and I can check whether it is a north pole or south pole. But this is the best method to check whether it is a north pole or south pole. So a freely suspended bar magnet aligns in the north-south direction because of the Earth's magnetic field. Okay, so now here comes the introduction about electricity and magnetism, because our topic is electricity and magnetism, right? Magnetic effect of electric current. So how come this is the beginning of electricity and magnetism or magnetic effect of electric current? We know inside the earth a lot of materials are there in the molten state, right? So this molten state, when we say at high temperature, the ions will be moving. Ions means what? Charges, right? Positive ions and negative ions will be there. So charges are moving. Whenever charge moves, we have learned in the first chapter, motion of the charges, it creates a current to flow, right? So there is a current, okay? So that creates the Earth's magnetic field. And now we are moving on to the actual discussion of electricity and magnetism. So the most important thing is Oersted's experiment. Its scientist name is Hans Christian Oersted. So he is the person who identified whenever electricity passes through a conductor, there is a magnetic field created. So he was demonstrating some electricity experiments to his students, and there were a lot of electricity materials on the table. And he just saw the compass needle which was kept there, it was reflecting. It was an accidental discovery, we can say like that. It was not a purposeful discovery. What's the difference between those two? See, normally we feel, see, when we go to the school lab, we have a set of experiments, right? We know we are going to write the aim of the experiment, what are the materials to be used, what is the procedure, and we do the experiment and tabulate the data, then find out the result. And in most of the experiments we do in our school, we know what should be the result. For example, if we are calculating the acceleration due to gravity, we know the value is 9.8 meter per second square, right? Acceleration due to gravity value is known to all of us. So we will be doing a simple pendulum experiment and we are going to find out the value. And if the value is not reaching to that 9.8, we are sure, right? Our answer is wrong. So that's the difference. We know the result and we are just trying that experiment. But this is a discovery, right? He was doing some other experiment and he found out something else, an unexpected thing, and that changed the whole world. So, how it is changing the whole world? See, most of the electrical devices we are using nowadays, it works on this magnetic effect of electric current. The magnets I have shown you, this bar magnet and the horseshoe magnet, the strength is very less. Okay, it's not even, we cannot make that into a very strong magnet as our wish, right? But if you have a magnet created using electric current, you can change the strength, you can change the polarity. See, if I have this magnet and I want this side to be, no, see, this is north pole, and I feel okay, I want this side to be south pole. It's not possible. Even if I cut this magnet, say I'm just going to break, I cannot break it now, I'm saying, see, if I break the magnet, still the north pole will be this side, south pole will be the other side. Okay, that's a property of a permanent magnet. Even if you cut it, there will be two poles. We call it as magnetic dipole. Okay, dipole means two poles. Okay, so let's come back to our Oersted story. He was demonstrating electricity experiments to his students, and he understood something is making the compass needle deflect. So something making the compass needle deflect. Compass needle deflects only if there is a magnetic field, right? Okay, so he understood this current which was flowing through the conductor, it was making the magnet deflect. Okay, so later on what he did is he made this experimental setup. This diagram looks very simple, right? We can say the simplest electrical circuit. There is nothing in that. There is a conductor and a battery is there, a key is there, a resistance is there. We can connect a rheostat also. Okay, so he switched on the circuit. He saw there is a deflection in the compass needle. Switched off the circuit, compass needle comes back to the original position. Then what he did is he reversed the direction of current. How do we reverse the direction of current? We interchange the polarity of the battery. Okay, the negative and positive sides, that is interchange. So definitely we know that current flows from positive to negative end of the battery. So when we interchange that polarity, then the direction of current is reversed. When direction of current is reversed, then the deflection was opposite. The deflection in the compass needle was opposite. So that means when there is a change in the deflection, that shows that the direction of the magnetic field is different. So these were his observations, and he increased the amount of current. Then the deflection was more. Decreased the amount of current, the deflection was less. So these were the steps done by Oersted in his experiment. So this is our board exam question. Let's come to our exam point of view also. So question can be explain Oersted experiment. The question can be for 2 mark, 3 mark and 5 mark. Same question. So how do you answer that? So Oersted experiment, simply if you are asked to write for 2 marks, you can say that Oersted, this diagram you can draw. It's a very simple diagram. It won't take less than 30 minutes, right? So just draw the diagram quickly and explain what happened. If it is a 5 mark question, you have to explain all these what I said in step-by-step manner. Because what are the possibilities? What you have to do? When it is switched on, what was the observation? When the current is switched off, what is the observation? When the current is increased, what happened? And when the current is decreased, what happened? All these things you have to write in a step-by-step way for a long answer question. Because see, and in physics or in any other subject, same question can be asked many ways. It can be for 1 mark, it can be for 2 marks, right? It can be a long answer question also. So be careful, read the question properly and start writing the answer. Okay. So this is our experiment, and let me show you how the deflection was observed, right? And how do you find out what is the direction of deflection? So now we are going to learn 3 different shaped conductors and what is the observation when current flows through that. Okay, so let's come to the Oersted experiment itself. There is a straight conductor. He has taken a copper wire. Straight conductor, no need to feel that it's something we cannot afford or we cannot see in our life. It's a copper wire. Okay. Any electric connection, you can see the copper wire. Take a copper wire. Connect a battery. Normal cell also, like a torch cell you can use. Then if you have a compass needle, you can try using a compass needle, or if you have iron filings, okay, iron filings are powdered irons, okay, that also you can use. And what you are going to do is just keep the conductor in a cardboard sheet. You have to insert the conductor into a cardboard sheet, then make sure it is stable, do all the connections, then switch on the circuit. So if you are using iron filings, you can see a beautiful pattern of iron filings. It forms into the form of a circle. Okay, so we are discussing about straight conductors. All these three shapes we have to learn in detail. It's very, very important and a repeated question in the board exam. See, I'm telling that because analyzing around 10 years question papers, you can see many repeated questions. And those who go to the exam hall after solving the previous year question papers, they feel very confident. That is a secret of, I mean, for most of the high scoring students. They do the previous year question paper. It's like, see, around more than 50 percentage questions will be repeated. Right. So we see the question beforehand, we know the answer and go to the exam. We feel more than 100% confident. So I'm giving you the questions now. See, it's not like if when I'm giving you the question, doesn't mean that only that question comes. There can be twisted questions also. Right. Now, nowadays we have the reasoning and assertion type of questions. They give two statements. So when they give two statements, we have to say first statement is true, second statement is true, and the second statement is the explanation for the first statement. So there are four options in that. We have to choose from A, B, C, D. So for 2 marks, we will be getting that question. Last year onwards, they have changed the pattern of question paper, right? So reasoning and assertion questions, very easy to score. As I always used to say, like MCQ questions, 1 mark will be gone if you don't read it properly. So if you have to answer those, see, it can be from physics, chemistry, or bio, right? So 1 mark will be gone if you don't read it properly. So one question will be the statement, second statement that will be, it can be an explanation for the first question or it cannot be. Maybe it is false explanation for the first statement. So if you have to think and answer that, you need to have a clear knowledge of the topic. Then only you can think whether it is a true statement or not, right? So here for a straight conductor, the magnetic field lines are circular in nature, concentric circles. We have to say they are concentric circles. Concentric circles means there are many circles with one common center. Okay, they are concentric circles. Then nearby the conductor, the strength will be more. Okay, and here you can see in the diagram, there is a direction shown, right? Definitely magnetic field is a vector quantity. It has both magnitude and direction. How do you understand the direction of the magnetic field? For that, we have a very interesting trick that is called as right hand thumb rule. So what is right hand thumb rule? We have to take a conductor. What I suggest is you take a pen or pencil. Okay. So the tip of the pen, let it be the direction of current. Hope I'm visible. You're going to take your pen. See, it is easily accessible. You don't need anything else in the classroom, right? See, you always have a pen. So the tip of the pen is representing the direction of current. We have to keep the right hand thumb in the direction of current. See, this looks like a straight conductor. So keep the thumb in the direction of current, wrap around the conductor. So the direction in which the other fingers are wrapping around the conductor will give you the direction of magnetic field. So remember, this is for straight conductor. Okay. So this is the trick to find out the magnetic field due to a straight current carrying conductor. So, right, according to right hand thumb rule, keep the thumb in the direction of current and wrap around the conductor, and the fingers which wrap around the conductor will give you the direction of magnetic field. Now let's try how to answer the questions. So we have, say, the current is in the upward direction. So now what happens? My fingers are wrapping around the conductor in the anti-clockwise direction. If the direction of current is downward, see how I'm going to keep my hand. It's right hand, make sure it is right hand. Thumb in the downward direction, wrapping around the conductor, you get a clockwise current. Say if they are asking in the horizontal plane, see, maybe from my right to the left. In that case, the answering is little bit different. Clockwise or anti-clockwise, we explain only for the vertical plane. Okay, if the conductor is the direction of current is upward or downward. If it is towards left or towards right, we have to answer it in a different way, but the trick is the same. We are going to keep the thumb in the direction of current. So what is happening now? My fingers are trying to go down, right? So if you are keeping this conductor on a sheet of paper, I'm just trying to explain you what is the concept of a plane, okay? So this conductor is on the plane of this notebook sheet, right? So when I do this, my fingers are trying to go into the notebook, right? Or into the page, or we can say into the plane. Okay? So, so if you are getting your fingers moving like this, then it is into the plane, into the plane. If the current is in this direction, my other fingers wrapped around the conductor will come from bottom to top, right? So what is happening here? It is trying to come out of the plane. It's trying to come out of it. This is going into. This is out of the plane. Hope you're understanding it. So this is how we apply the trick of right hand thumb rule and find out the direction of magnetic field. Remember, this is for straight current carrying conductors. So the properties of magnetic field of a straight current carrying conductor are they are concentric circles. Nearby the circle, the magnetic field strength is more. When you move away from the conductor, the strength is less. How do you increase the strength of the magnetic field here? You can increase the current. You can keep a conductor of same length and allow the same amount of current to flow through that in the same direction. Then the strength of the straight conductor magnet can be increased. Okay. Now, the next shape, I told you we have three shapes to learn. The next one is circular loop and another one is the solenoid. So magnetic field due to a circular loop carrying current. If you have any doubts on what we have discussed up to now, please type in the comment box. I will answer that. Okay. Now let's move on to the magnetic field pattern due to a circular loop carrying current. Circular loop, let's take a bangle or any circular material you can take for understanding purpose. This is just a wooden thing. Okay. So this is our circular loop and we have to put it inside a cardboard sheet so that we can plot the magnetic field. And we are going to connect the battery and the rheostat, everything we are going to connect. Then once you switch on, you can see a beautiful pattern of magnetic field line like this, right? This is so beautiful to see how this is happening. And how do we explain the field pattern here? So each circular loop carrying current can be considered as small straight conductors. Okay, it can be considered as small straight conductors. So if you break this bangle, you will get small pieces of these bangles, right? So that is a straight conductor. So I'm going to take two positions, okay, say A and B as shown in A and C as shown in the diagram. So two positions on the two sides. Let me say this current is flowing in the clockwise direction. So this current is going in the clockwise direction. So when it is in the clockwise direction, if I check one of the ends, say here the current is in the upward direction. When the current is in the upward direction, what happens? My fingers will be trying to go into this, right? See this. It's going to move into the circle. At the same time, when the current reaches to this side, my fingers will be going like this. Here it is trying to come like this, and here. This is the same way the magnetic field also moves. Field lines will move inside the coil. So, outside the coil, the field lines will be moving away from each other. See, I'm doing this because see here, the current is in the upward direction. So, field lines are like this. Here it is this way. But within the coil, if you see, within the coil, all the field lines are in the same direction. But when it goes outside the loop, you can see my thumb moving. That is the direction of magnetic field. Okay. So outside the coil, it will be diverging from each other. But within the coil, it will all the field lines will be in the same straight line, same direction. Okay. So when lot of magnetic field lines comes in the same direction, the magnetic field strength will be more. So, we know that the degree of closeness of the magnetic field lines indicate the strength of the magnetic field. So, when the field lines are close together, then the strength is going to be more. Hope you understood that. So here also, we can say inside the circle, especially at the center of the circular coil, the magnetic field strength is going to be more. Okay, then you can see a straight line drawn there, right? What does that straight line indicate? It is a magnetic field line with infinite radius. Okay, it's a circular magnetic field with infinite radius. Why did I mark it from south to north? Initially, I told magnetic field lines are from north to south. Am I correct? Here, the diagram you can see it's south to north. What is the reason for that? See, it is within the coil. Okay. Outside the magnet, any magnet when you take, as I said, magnetic field lines are closed curves. Outside the magnet, magnetic field lines will be from north to south. Within the magnet, it will be from south to north. This is how it goes. Within the coil, the magnetic field lines will be south to north because it's a closed curve, right? It's a closed curve. So within the magnet, it is south to north, and outside the magnet, it is north to south. These are all minute points when I say it's very important because when you draw a diagram, if it is a long answer question or a diagram is given and they ask us to figure out what is wrong in that diagram, we should have this knowledge. Otherwise, we won't be able to answer these questions. See, if you draw all these pattern and then you say, if you mark it wrong, if you mark the direction wrong, then the entire thing will be gone wrong, right? So make sure all the concept is clear so that you can draw the diagrams independently. So practice this diagram. This is again a repeated question in our board exam. When I say it is repeated, it is definitely, I mean, it is a repeated question and it is, see, the percentage, the probability is more here, okay? Now, this circular coil carrying current magnet, it behaves like a disc magnet, like a coin. What do you say? We can take the lid of a bottle, right? That or a coin. Coin is the best example, I feel. So the coin has two sides, right? So let me take my bangle again. So if the current is flowing like this, I'm observing from this side. What is visible for you is from the other side, right? So let me give you a small activity. You just draw a circle in your notebook. Even let me also do that. So we are going to draw a small circle, okay? Draw a small circle. Small circle is drawn and put a clockwise arrow. Put a clockwise arrow. Then turn the page. Turn the page, you can see the impression of it. Right? You see the impression of that circle I made. When you do it in your notebook, it will be clearly visible to you. See, my circle is here. I put a clockwise arrow. Turn to the back side. You see the impression that will be in the anti-clockwise direction. This is not related with magnetism. This is just a simple demonstration how that position is changing to understand how how you see the things, right? Hmm? We always say in real life also we say we have to think from the other person's end also. Don't always think from your side, right? Think from the other side also. See, I'm seeing, say for example, I'm seeing the current in the clockwise direction. You will be seeing that in the anti-clock. For you, it is anti-clockwise direction, right? So, to identify the polarity of a magnet, you are going to look at the magnet and see in which direction the current is flowing. If the current is flowing in the clockwise direction, that is the south pole of the magnet. If the current is in the anti-clockwise direction, that is the north pole of the magnet. Okay, so south pole and north pole can be identified by observing the direction of current. It's very important you get diagram based questions. Okay, when it is diagram based questions, they just give the direction of current. We have to identify the polarity. Very simple, easy to score. So you just have to check whether the direction of current is clockwise or anti-clockwise. If it is clockwise, if it is means, I've seen many times students used to write if it is clockwise. What do you mean by if it is? See, when I'm explaining initially it told if the current is, okay. So you have to write if the current is in the clockwise direction, that is the south pole of the magnet. And if the current is in the anti-clockwise direction, that is the north pole of the magnet. Okay. So those who has written is if it is clockwise and if it is anti-clockwise, I'm sure they'll be laughing now, right? No, that's a common mistake we do because the answer will be there in our mind and automatically we write whatever we feel. Okay. Now, one more thing related with the circular coil. If you increase the number of turns instead of a single coil, if you use a lot of coils, okay, and make sure the current is flowing in the same direction, then the strength can be increased. And then increase the current. Increasing the current is the same. It's a common method to increase the strength of the magnetic field. Okay. Then another method is take a circular coil of smaller radius. See, I have a bangle here. Take a small bangle. Bangle in the sense a metallic thing you have to take. I'm just giving you an example. I don't have a circular coil here to show you. Okay. So take a coil of smaller radius. Then the strength will be more. Now let's move on to a solenoid. Okay. Solenoid. You can see the beautiful pattern of the magnetic field line here in this experiment. Hmm. Current is shown, current is flowing through the coil. See, what is a solenoid actually? What is the difference between a solenoid and a circular coil? Circular coil, the what do you say, the coils, the conductor coils will be very close to each other. And here, see, the both are made of copper wires. In a solenoid is in the form of a cylinder. Coils looped in the form of a cylinder. Copper wire, we say that it's insulated copper wire wound in the form of a cylinder is called as a solenoid. Okay. So what's the difference there? There will be some different distance between each coil. Circular coil having n number of turns, they'll be close to each other. It's like a compressed form. But this is like a spring. Okay. That is how you can identify a solenoid and a circular coil carrying n number of turns. Okay. So when you allow the current to pass through a solenoid, then it behaves exactly like a bar magnet. All the magnetic field pattern and the properties, everything is similar, exactly same as that of a bar magnet. But there is a difference in the sense a solenoid magnet we can increase and decrease the strength, we can change the polarity. Okay, see, if I need a very strong magnet, I can increase the current. If I decrease the current, then the strength will be decreased. Okay. And if I want the north pole to be changed as south pole, just reverse the polarity. Definitely it will be changing the polarity. So that's the advantage of this solenoid magnet. And definitely, like how do we increase the strength? See, all these states we have to say how this is going to increase or decrease the magnetic field. That's another separate question. What are the methods to increase or decrease the strength of the magnetic field? Okay. So here another method to increase the strength of the magnetic field of a solenoid is you can insert a soft iron core material into that. Okay, soft iron core material. You can see here, soft iron is a magnetic material. Okay, so it can be inserted into the coil. So the soft iron also get magnetized. So the strength will be increasing in that case. Okay, so these are the methods to increase the strength of the magnetic field. Now let me show you a beautiful picture here. This is how the solenoid magnet's magnetic field lines looks like. Here another important thing is inside the magnet, the magnetic field lines are straight parallel lines. That means they are uniform in nature. Okay, so magnet. So how do we explain the solenoid magnet's magnetic field? This it's very similar to that of a bar magnet. Outside the magnet, the field lines are from north to south. Within the magnet, see, in the case of bar magnet, we were not able to plot the magnetic field line within the magnet, right? So in case of solenoid magnet, we can plot it. That's the difference. Okay, because there is an empty space, we can move the compass needle or we can allow the iron filings to go through that. It will be increasing. Okay, the strength will be, the pattern can be seen. So it's uniform. That is again a repeated question. When I say repeated, you have to note it down because these are the board exam questions I'm giving to you, previous year board exam questions. Explain the property of a solenoid's magnet inside it. Okay, inside it is uniform. Even it comes in MCQ. If you see the NCRT exemplar questions, they say find out the incorrect statement. There was a question, incorrect statement. They give a lot of correct statements. Among that, we have to find out which is not correct, right? So they say in one of the questions, what I have seen is they say that the magnetic field inside the solenoid is of zero strength. That was the incorrect statement. NCRT exemplar questions, I've made a separate video. I can give that link in the description box. Okay, those who have not seen, you can watch that. Because those are the score makers of our board exams. Especially MCQs, very important, very good MCQs are there in exemplar questions. Last, see, the latest 2020 exam, 3 sets of question papers, everything was there from the exemplar questions. Not even a single question outside that exemplar questions. The exemplar questions are the questions given by the NCRT publisher itself. I mean, from the CBSE board itself. Okay, so we are supposed to know that, and the same thing even without changing the value, they have asked all the questions from the exemplars. So make sure you see that and learn it. Okay, so inside the solenoid, the magnetic field lines are uniform. Uniform means how do we represent it? By drawing straight, parallel, equidistant lines. Okay, so this diagram clearly shows how the magnetic field of a solenoid looks like. Now we are almost done with the different shape current carrying magnets. Where do we apply this? Where do we apply this electromagnet? We call this when you have a soft iron as the core material, you can call it as an electromagnet. Electromagnet means it acts like a magnet if current flows through that. It will not be a magnet if we switch off the current. Okay. Now another important question we can expect here is, if you use steel as the core material, what will happen? Why can't we use steel as the core material for an electromagnet? Electromagnet, the name itself says electromagnet. It is a magnet only if electric current flows through that. See, we need electromagnet because we need to use the magnetic properties according to our convenience, right? Whenever I need magnetism, I can make it a magnet. If I don't need magnetism, then I can switch off the circuit and it loses its magnetic properties, right? So, if you are using soft iron as the core material, it gains magnetism and it loses magnetism the moment we switch off the current, it loses its magnetic properties. But if you are using steel as the core material, if the steel is used as the core material, then steel will gain magnetism, but it retains its magnetism. It will not lose, it will not give that magnetism back. Like some kids, right? If they get something, they will not give it to anyone else. Steel is like that. But iron, soft iron is very liberal. Soft iron will give, if it doesn't need, okay, it will just lose its magnetism. It's soft iron is ready to give up the things, right? Steel will not do that. So steel can be used to make permanent magnets. Different shaped magnets, what we see nowadays, is made of different types of steel depending on our requirement, because sometimes for industry purpose, right, and then some building construction areas and all, we need different types of magnets. So the requirement is different. In medical field we are using magnets, right? and in industries we are using magnets. So different areas we need different types of qualities of the magnet. So accordingly, different varieties of steel are used to make permanent magnets. Okay, so why can't we use steel for an electromagnet? Because steel will retain its magnetism, it will not lose its magnetism. Once it gains magnetism, it becomes a permanent magnet. That's the property of steel used as the magnetic material. Let me show you a very simple device which uses electromagnet in it. This is our electric bell, the school bell, the most expected sound, right? Especially around 12 o'clock, we'll be expecting this bell. Has anyone thought of how it is working? Again, physics is there in that also. Okay, so it works on magnetic effect of electric current. There is a U-shaped magnet, and that is a horseshoe magnet. Horseshoe magnet, in sense, it's not the horseshoe magnet I have shown you. This horseshoe magnet I have, that is a permanent magnet. Okay. It's a permanent magnet. I cannot change the strength. It cannot lose its magnetism. If I throw it, if I break it, I do whatever I want, it will have its magnetism inside. Maybe the strength may decrease. Okay. So I don't have any control over this. But if you use soft iron core material and construct an electromagnet like this, then there is a hammer, and this is called as gong. Okay, the A is the hammer and B is the gong. So the moment you just observe what is happening there, when the switch is on, there is a current flowing in the circuit, right? Switch is in the on position, current flows through the circuit. Then whenever current flows through that, that becomes a magnet. Whenever current stops, it becomes, and it's not a magnet, right? So when it is a magnet, that U-shaped magnet will be attracting the soft iron armature. Then the screw is detached from there, right? The screw is detached. Screw and the connection is detached. Then it becomes a open circuit. When it is an open circuit, there is no current flowing, it's not a magnet. So what happens? This comes back. When it comes back, it becomes a closed circuit. Again, it's get attracted. So this is how the electromagnet works. So this is one of the instruments we where we use electromagnetism or an electromagnet in real life. Okay. So the magnetism, the characteristics of the magnetic field, all those portions are done now. Let me know if you have any doubts related to this. Please type your doubts in the comment box. Okay. So now let's move on to the next topic. That's force acting on a current carrying conductor kept in a magnetic field. Force acting on a current carrying conductor kept in a magnetic field. If you have a current carrying conductor, this is the experimental setup you can see here. So you have a horseshoe magnet and a conductor, a straight conductor. Okay. So I'm going to suspend that freely in the magnetic field of a horseshoe magnet. How do we do that? Let me just show you. Let me take this as the horseshoe magnet, and let me take any pen as the conductor. Okay. So this is how we keep the conductor and the horseshoe magnet. So we are going to keep the conductor in the magnetic field of a horseshoe magnet. Okay, try. I hope you are able to understand how the experiment is done. So this is, imagine this is my horseshoe magnet. I have a real horseshoe magnet also. So we are going to keep the conductor in the magnetic field of a horseshoe magnet, and it's free to move. Okay, this conductor is free to move. We are going to suspend it. So once the moment you switch on the current, what happens is this conductor will deflect. It shows, see, initially say for example, if this is in this direction, once I switch on the current, it deflects. It deflects in the sense it deflects in a particular direction. It deflects because there is a force exerted by this horseshoe magnet on this current carrying conductor magnet. Because when current is flowing through that, it becomes a magnet, right? So there are two magnets now. One is the horseshoe magnet and the other one is the current carrying conductor magnet. When two magnets are there, one will be exerting a force on the other. That is what is our topic now. Okay. So force acting on a current carrying conductor kept in a magnetic field. So a current carrying conductor kept in a magnetic field will be experiencing a force. And in which direction it moves? We can find out the direction of motion using Fleming's left hand rule. Already we learned one rule with our hand, that was right hand thumb rule. That is to find out the direction of magnetic field of a straight current carrying conductor. Right? Even we have learned the clockwise rule, that is to find out the polarity of a solenoid magnet and a circular loop magnet. Here it is Fleming's left hand rule. So Fleming's left hand rule is to find out the direction of motion of a current carrying conductor kept in a magnetic field. Okay. So we have to take our left hand, keep our thumb, forefinger and central finger in mutually perpendicular directions. What do you mean by mutually perpendicular? See, these two fingers are at 90 degree with each other. These two fingers, if I check, they are at 90 degree with each other. If I see these two fingers, they are at 90 degree with each other. Right? So all the three fingers should be like X, Y, Z axis. In maths, you draw, in geometry, you draw the three mutually perpendicular axes, right? So keep the three fingers in mutually perpendicular directions such that the central finger, right? The central finger indicating the current, then the forefinger or the pointer, forefinger indicating the direction of magnetic field, then automatically the direction in which the thumb shows, that gives you the direction of force or motion acting on the current carrying conductor. Okay. So keep the central finger in the direction of current. I specify it is central. You can remember this because these three terms and the fingers are very important. Central finger C. Okay. That is how you can memorize it. That is a trick. Central finger C. Current. Okay. So central finger in the direction of current. Forefinger. Most of us use the word pointer. I am not using the word pointer because we have to relate and learn. Okay, forefinger indicates the direction of field. F, forefinger, F, field, F. So forefinger indicates the direction of field. Then the thumb, automatically the thumb will be pointing in another direction. That gives you the direction of motion of the conductor or direction of force acting on the current carrying conductor. Okay, so this is the trick to find out the force acting on a current carrying conductor. You will get application level questions on this. The direction will be given. Sometimes what happens is they give the direction of the question can be like a stream of alpha particles moves from east to west. When you see that, what do you mean by alpha particle? I have never heard of alpha particle, right? Alpha particles are positively charged particles. A stream of alpha particle means positive charges are moving. Immediately you have to think positive charge motion, that is the direction of current. If you see a question like a beta particle is moving in this particular direction or an electron is moving in a particular direction, beta particle and electron represent negatively charged particles. So, whenever there is a direction of negatively charged particle given, you have to take the direction of current as opposite to that because we know direction of current is from positive to negative, right? So, it is opposite to the flow of electrons. So, you have to think accordingly, keep your fingers accordingly and find out the direction of motion or the direction of force acting on the current carrying conductor. Now, where do we apply this in real life? We have the electric motor. Electric motor works on this principle. So the force acting on the conductor can be increased by increasing the amount of current, increasing the strength of the magnetic field, increasing the length of the conductor kept in the magnetic field. There are so many methods to increase the strength of the, to increase the deflection or increase the force acting on the current carrying conductor. Okay. So, electric motor, it's a device which works on this principle. So, what is a motor? Motor is a rotating device, right? It converts electrical energy into mechanical energy. See, this is again a long answer question for 5 marks. Explain the construction and working of an electric motor. So this year in CBSE they have removed generator concept. So generator, it's only because of the pandemic they have reduced the syllabus. Otherwise, generator also will be there. Definitely, those who opt for science in higher grades, this generator also will be there. But for this year students, definitely generator is not there for CBSE. But Kerala State has not reduced the syllabus. They have to learn it. Only for CBSE students, generator is eliminated. Okay. So, motor works on this principle of force acting on a current carrying conductor kept in the magnetic field. Okay. So, how does it work? Hmm? How it is going to work? So, let's see the construction of an electric motor. What are the parts of an electric motor? Definitely, it works based on the magnetic effect of electric current, right? So, there should be a conductor which is kept in the magnetic field. So there are, you can see two N and S, right? That they are the north and south pole of the magnet. And there is a rectangular coil that is called as the armature. You can see A, B, C, D, right? That's the armature. So what is armature? It is a metallic coil wound round a soft iron core so that it is free to rotate. It is fixed firmly on the axis XY. So it's a rectangle, copper wire made into the form of a rectangle. Okay, that is the armature. So in a commercial motor, this is just a demonstration. So in a commercial motor, there will be coils of many turns. Okay, so we know when there are a lot of turns, there will be an increase in the current and increase in the magnetic field strength. So that all make a difference in the speed of rotation. Okay, so armature is a part, and another one is the horseshoe magnet, the strong horseshoe magnet, then axis, then we have the split ring, very important thing, split ring commutator. Split ring commutator, what do you mean by split ring? I have a ring, I cut it into two semicircular pieces. Okay, they are called as split rings. So we name it a split ring commutator. What do you mean by commutator? Commutator is a device which reverses the direction of current in a circuit, which changes the direction of current in a circuit. Okay, so split ring, armature, magnet, the most important battery, because electric motor is a device which converts electrical energy into mechanical energy. So if we have to convert electrical energy to mechanical energy, there should be something which provides electricity, right? So battery is most important. Then split ring commutator and brushes. Two brushes are there, two carbon brushes are there. So the allotrope of carbon, which is graphite, which is a good conductor of electricity, that is used as the brushes here. And let me give you some questions from here, because all this chapter discussion is done already, right? So the important questions are, the type of questions are, 2 years back that what the board has asked is, two parts of the mottos were given. So, as all of you know, there are three sets of question papers every year. So each question, each paper, it's not shuffling the numbers. Okay, those who are not aware of this board's pattern, let me just explain to you. There are three sets of question paper in your classroom. Your friend may get one question paper, you will be getting another question paper. And it's not like in the competitive exam. Competitive exams, they're going to shuffle the question paper, question numbers, so that they can avoid copying, right? It's not like that in our CBSE exams. The questions will be completely different. Okay. So if your friend got motor, you may get generator question. If your friend got circular coil experiment, you in your question paper you can see the solenoid question. Questions will be different. Understand that first. Okay. So the question pattern, see, the importance to each chapter will be the same. The preference, the percentage of mark given to all the chapters will be the same, even though the questions vary for each child. Okay. So the level of difficulty also will be the same in each question. Okay, so that doesn't matter. The question is different for him or her. That's okay. So the pattern of question was they give two parts of the electric motor or the generator, and you have to explain what is the function of it. For example, if you are getting a magnet and an armature. Magnet, what is the function of the magnet? To provide a strong magnetic field. Armature is to rotate. It is the conducting, current carrying conductor which rotates in the magnetic field. Right? That is a rotating device. If you see the split ring is used as the commutator. So the commutator's function is to reverse the direction of current. And brushes acts like the conducting path between the battery and the armature. So these are the parts of the motor, and there will be an axle. So let me show you a textbook diagram here. You can see the axle. This axle is the one which rotates, and what we can see, right? So that is the axle. See, where do we see these motors normally? Motors are seen in all the in our house itself. We can see the fan, then mixer, grinders, washing machines, and all those devices. We can see this motor. Motor, see, when I say we can see the motor, it's not real motor we are seeing. We see only the rotating part. For example, in the fan, we see the leaf rotating, right? Within that, there is a motor. Okay. So this is how the motor works. See, there can be a question for 5 marks. Okay, explain the construction and working of an electric motor. So now let's see how can we explain, how can we understand that. We have a battery connected here, right? This battery has, see, first of all you have to observe from where the current flows. Okay, so when current is flowing, it is from positive to negative end of the battery. So initially the current flows from the arm A to B of the rectangular coil. Say for example, let me take this as the armature coil. So this is the side AB and this is side CD, right? So current enters into the coil from A to B, then C to D. So what we have to do here is we have to apply Fleming's left hand rule. Okay, so current is from A to B. So which finger we have to take? Left hand central finger in the direction of current. In which direction is the magnetic field? Magnetic field is from north to south. So what happens is this is the current, and so I'm keeping the direction of current. Then this is the direction of magnetic field. So what happens is my thumb is moving downward. So I applied the Fleming's left hand rule, and I see that my thumb is moving downward. When thumb is moving downward, we have to understand that the side AB of the coil is moving downward. Okay. So when AB moves downward, automatically CD will be moving upward. Okay. So otherwise also we can find it out. Current is flowing from C to D. When current is flowing from C to D, I have to keep my central finger from C to D. Then magnetic field is always from north to south. Right? So north to south, forefinger from north to south. So thumb is moving in the upward direction. And remember, it is left hand. We are talking about motor, right? It's left hand. So thumb is in the upward direction. So side CD of the motor will be moving upward. So AB moves downward and CD moves upward. So what happens now is brushes are stationary. Which part of a motor is stationary? That is another question for 1 mark. So the brushes are stationary, the carbon brushes are stationary, split ring will be moving. Split ring will be moving along with the armature's arms. Okay. So when AB moves, along with that, the split ring P will be moving to the other side, as you can see in the video, right? So it will be moving to the other side. And at the same time, the combination of brushes and the split ring will be changing. So in the next half rotation, when it is half rotation, see this goes down and CD comes to the place of AB and AB comes to the place of CD, right? During the half rotation. So now the current flows from D to C and B to A. So initially the current was from A to B. Now the current is from B to A. In the first half rotation, current was from C to D. Now it is from D to C. So this is how the split ring is changing the direction of current. Okay, so that is why split ring is called as the commutator. Split ring is called as a commutator because it reverses the direction of current in the circuit. So this can come for 5 marks. Okay, explain the construction and working of an electric motor. So when you are asked to explain the construction and working of an electric motor, that means you have to say from the beginning, you have to explain what is the principle of it, what type of energy conversion is happening there. Electric motor converts electrical energy into mechanical energy, and then you have to start, you have to draw the diagram is mandatory. You have to make sure you label it correctly, all the parts, like from the magnet, then the armature, the split rings and the brushes, and most important, don't forget the battery. And never by heart what is happening here, you learn and write it, because in case when you draw the diagram, if the polarity of the battery changes, the complete explanation will be the reverse order. So make sure you learn how it is working, then write it in your own words. It's not mandatory to by heart anything and write here, because it's a functioning of a device. You have the freedom to write it in your own words. Okay. So learn how it is working. So most important keywords here. First thing is the conversion, right? Electrical to mechanical energy. Then marking the parts of the motor, make sure everything is there. Splitting, you have to specify it is a commutator. You have to write commutator is a device which reverses the direction of current in a circuit. That is mandatory. Then you have to write brushes are stationary. It will not move. It just acts like the conducting part. Split ring. Okay, split ring is important. It's a complete ring split into two halves so that it can rotate along with the armature. So make sure all the polarities are correct before you start explaining the functioning, and Fleming's left hand rule should be there in your answer. Even though it is there in your mind, I have seen many students don't write that in the answer sheet. So you have to write, apply Fleming's left hand rule. Then you see that the arm AB moves downward and CD moves upward. So write what happens in the changes happening to the split ring and the brushes combination. So that is how we are going to explain the functioning of the motor. So this is again a 5 mark question. So almost all the important topics are revised now, and some of the, electromagnetic induction and the household circuit, they have eliminated from the syllabus. It's there in the textbook, but it is eliminated for this year's students. Hope they will not again include it. As of now, it's cut from the syllabus. Okay, so we are not moving to that. Already in the classroom and the videos, I have explained all the entire chapter is explained. Since it is a revision, we can just go according to the exam point of view. Okay, so those who need again the explanation for generator and household circuit, I will be providing the link for that video in the description box. Okay, so if you have any doubts, just open it for a discussion now. If you have any doubts, please put your doubts in the chat box. We can clarify those doubts. So after that, we can wind up today's class. Okay, so all of you will be in the festival mode, right? Okay, so let's wind up today's session now. So once again, wishing you all a very, very happy Diwali and a very happy Children's Day to all my students. Okay, so if you have any doubts, you can mail me. You can send a mail to sudha.adu2005@gmail.com. Let me just type my mail ID. So you can send if you have any doubts. Okay, so I will be replying, and or if lot of doubts are there, I will be clarifying that in a separate class. So hope this today's session was useful for you. So once again, wishing a very happy Diwali and happy Children's Day. Thanks for joining and thanks for watching the session.